Okay, I think it's okay for the volume. Okay. Well, welcome again to the series of RISC-V tutorials. I am going back here now that I have a little time. So, yeah, last time we did a lot of stuff to actually just blink a LED. Actually, I am blinking a LED right now in the system. I did some additions to the system, like a simulator and the support of C code. In the meantime, I didn't put too many details about that because, I mean, it's kind of trivial, but it's just a matter of putting the same as code, the same. Let's see the RISC-V code that initializes the memory, initializes the BSS section. Then it just loads the arguments and calls the main, and then the main is the one that you think. The program is exactly the same. I mean, is the GPIO stuff. So it's just a matter of putting knowing where's our GPIO, then assigning registers to the registers to make it blink with a little wait time, the same that it was in the last one. So just like the title says, I am going to try. I don't know if I'm going to be succeed, but I'm going to try putting a single data RAM, a single data RAM, or SDRAM. Now, in the ULX, that is the this shell that we are working on, the SFPA. It's advertised to also have a DDR. Now, if we have a DDR, that means that we can have more memory. That means that the memory space for running Linux will be enough. So this will be an essential step to make run Linux on this FPGA. So without further ado, let's get started. I mean, I did a little of digging for the memories. I have seen this one. It seems promising. I mean, it's just one model, and I love one model implementations. And it's very simple for an implementation of an SDRAM controller. It can control a lot of parameters, which is good. Just supplying what is the megahertz of the RAM, and the address, the column in the bank, and that kind of stuff. And the ports. The ports is a very simple interface. It's a wishbone interface. We'll talk about that later. And the SDRAM interface. Now I have seen another ones as well. This one is a little more complicated, and it has configuration bits. I don't know if this configuration bits will be relevant, but I see this is so much more complicated because it has a lot of files. Yes, it has a lot of stuff here, like testing. There's a lot of stuff here that I don't know why they needed all of that. Maybe it's because they support more data. I mean, this one is advertised to be like 193 mega transactions per second or something like that. This one is just an simple implementations. Then again, remember that we are doing a simple implementation. If we need a speed, or we need some kind of special stuff, maybe we can resort to use a more complicated one. So that's for the memory. So we are going to choose this one. Now I'm going to save this SDRAM into our project, which that is RISC-V console. Where's the RISC-V console? I see it, RISC-V console. And go to FPGA. Sorry, no. Let's go to the hardware and the RISC-V console. And now we are going to create a new folder that is named resources, and I'm going to create another folder that is going to be named SDRAM, and we're going to save all file here. So what is going to happen is that the way that we are going to do this is reference this model just as it is, from the Scala environment. So in order to actually make it like automatic, we can just like put it there, then it will be copied and referenced automatically in the list of files to compile. So we just need to create the environment for instantiating this as the RAM. And this is what I'm going to do. So I already created this package named devices, and I was about to create another new package for the SDRAM, and we are going to put everything about the SDRAM related there. Now I'm going to put a file here that is named SDRAM.scala. Yeah, very creative. And now this is going to be, I mean, we put this in RISC-V console, we put this in RISC-V console.system. So this one naturally will be in devices.sdram, no? Yeah, something like that. Very simple. And the first thing that we are going to do, besides importing the HSL3, is to actually make it work with the Scala environment first. That means that we need to actually import it. Maybe this is too little. Shit. I need to the editor. I need to change a little the editor stuff. Using font. Let's put it into 14. I think this is legible enough. Yes. This is being transmitted in HD. It's, I think, yeah, because actually having it too small maybe is too inconvenient for me, but too small is very inconvenient for my viewers. So maybe like this. Okay. So the way that this is done is we need to create a class. Actually, we are going to create two types of class. We are going to create a case class for the configuration file, so for the configuration trait. So this is going to be the SDRAM black box config, and we are going to store here a lot of stuff that maybe we are going to need for the parameters. Like what kind of parameters? This kind of parameters, because I mean we can put all the parameters separated in a comma, but this is more convenient. Like just put it double T all here. And this is just for handling inside of the of this configuration when the model will be created. Now we are going to do just a class here, name it SDRAM, which is the SDRAM resistance, a black box. Now for the black box, so we need. We are going to put here the parameters that we need, and the parameters that we need is the configuration. So I'm going to put it in conveniently in a CFG variable that is going to be type of this, for example. I'm going to make it val, so it is permanent within this class. That means it's not going to be changed once you put it inside of the class. For like all the modules, like all the modules, you need this to have an IO that is an IO of a new bundle, and you put your ports here. Now you can make it like this. I mean, I put all the things here, but maybe we need to separate, like, the wishbone interface and the SDR interface in separated traits. So we are going to choose that. So class, for example, trait. Those are traits, I think, you know. Trait, SDRAM interface, and we're expecting that this is a bundle. Yeah. Then we are going to put all of this in the notation of the stuff. So I'm going to copy it for here for now. But yeah, I'm going to put this like vol this thing, then put this an output pool. Yeah, so you get my drill. It's something like this. And I'm going to do the same for the other ones that are there. So CKE, CS, RAS, CAS, and WE. Simple enough. Now vol SDRAM DMQ, which is again an output, but this output is uint, you know. Again, if you don't know about this, maybe you need to do the tutorials for chisel. I mean, I'm going this fast because I am instructing to you the system integration rather than actually the how to deal with Scala. So we're going to put this here. This is these 2 bits. This is 13 bits. This is 2 bits as well. And this is not an output, so this is an in-out. But then not an out, so it's name it like analog of 15.w. And we need to import this. Okay, it's not anymore. No, it's an experimental. Okay. There you go. This is our bundle, the part of the bundle that is for this. And then we are going to do the same for the other one. That means that we need to do the other trait, that is the by the way, this is a trait, so this is a has, and I'm going to name it maybe better like this: SDRAM interface. So this has SDRAM interface, and this is has wishbone interface. Again, we do the same again. So the only thing that we care about the interface is this. So let's do it with that. This is not close, and this was close here. Then we do the same again, but instead is named it like this, and it's an input. Then we have like WE and the cell. The cell is not a bool, it's a new int of 2.w. No, sorry, it's not 2, it's 4. The cell, the CEC, the address. I mean, the address is more like this. The address, the data, and the data of output, this thing, and this other thing. So input. Address is not 4 bits, is 32 bits, and this is 32 as well. This is the other one is also 32 bits as well. Install and acknowledge, but acknowledge is an output. Same for install. And we are ready to go. Here we go. We are good to go. Very simple wishbone interface. That means that wherever they put the selection and the CGC, sorry, the CGC more than anything, it will respond. It will be asserted until the ACK will be there. I don't know what about the stall. I need to know what the stall does. I know how to handle very basic wishbone interface. I'm more used to RISC-V and the iLink, but yeah, let's do it. Now this is going to be a bundle, so I'm going to put a bundle here. So it's a new bundle, no? But I'm going to put both of them here, with the wishbone interface. So this I/O will have like everything there, just right there. And we need a clock and a reset, no? Clock A and reset I. So clock 0KI, which is an input of clock. And the reset is an input of boot. So we will have all these two, this thing and this thing. Simple enough. Now we already handled the ports, so we are going to handle the parameters now. The parameters, for the parameters you need to do it like this. You need to put a parameter inside of the black box, and you see that it will ask me for a map of strings. So the strings are this. Then you put parameters inside of each mapping. So we are going to do just that. So map, you put a string, then you map it to the for example, like in param. Now this is not imported, so I imported. So it's here. In param, and the in param is going to have a value, and the value is 50 by default. So we can just do this with a lot of stuff, but for some reason we have this configuration here. So the configuration here can be passed to this map. So we are going to create in parallel. Sorry, I'm going to close all of this. I'm going to create to create in parallel each one of the parameters. So this will be the SDRAM megahertz. SDRAM megahertz, which is a big int equals 50, and so on and so forth. Now I'm going to put this conveniently like here in some place, so like this. I'm going to delete it later. And we have this. So we already deal with this. We are going to do this, the other ones. So there's a lot of calculated ones, so we actually only need like 5 of them. Then we calculate the rest of them. I mean, we can calculate them or leave the Verilog to handle this. But I think it's safer for us if we do it inside. So we are going to just do it like this. Okay, there we go. So address with it, and the default is 24. Then column with it is 9. Then the bank W is 2. and the DQNW is also 2. Perfect. Then we create the same again for this one. We have to separate it by comma. Then do the rest. So you see all of this gets initialized to 50. Now we can use the CFG instead of that. So this is megahertz, right? I can just put it here and it will work. And now we need the calculated ones. So the calculated ones are not supposed to be parameters. Maybe they are meant to be calculated. So we can just put it here inside of the case class. After you supply this, we will calculate this ones just inside of the configuration stuff. So this will be the banks is SDRAM is 2 to the power of that. So an equivalent will be something like this. I think so. Yeah. I think this is the equivalent. We don't use power here. The row is this. The next one is refresh count. Refresh count, which is this. Okay, again, it's not 2 to the power, it's 1. Just place it there. Again, big. Maybe I need to do big int of 1. But it's not big int. What is the problem here? Okay. The second parameter is supposed to be a thing. Okay. Maybe that is okay. Then we continue. No, we are in start delay. Now start delay. Start delay is whatever is this. Thing like this, okay. Start delay, start refresh. This is this. And the real latency is 2. It can be a parameter here, but we will see. And now the SDRAM, the SD target. Holy shit! I actually didn't read this. Where's this thing used? So if the SDRAM target is silenced, they use DDR2. Okay. Or otherwise, it will use something like this. They have a default. Okay. So I need to put something that is not silenced. And this will be a parameter. This is a string, no? So this is equals to generic. Let's put generic. And that's it. That's how you do this. I mean, we're still missing the other ones, so we shall put them here. So we are in DMW. So banks is the next. Banks, row. Refresh. Start delay. Refreshes. latency, and the target, which is not an int param. This is a string param. Also, you can import it as well, but this is not from core. Maybe it's from here. So there is an integer, and no, we need to put it here. Perfect, we are ready to go. And this will create the black box. So we already have the black box like complete, finally. And we can start to do our implementation of this stuff. So I'm going to open here one of my projects, but I'm not going to show it. I did a conversion from Wishbone a little while ago. But then we need to also do a configuration file. So we need like the configuration file for knowing the memory. We're going to attach the memory. So I think we are going to do it in the same way that we do all the time. So that means that we are going to do a peripheral. So we are going to start to do the peripheral. Okay, so for the peripheral, maybe we need to start by creating the key. So the key is I'm going to show you what is a key. A key is this, is that kind of stuff. For example, this is a key, this is a key, this is a key, and each one has, you know, like parameters to be assigned. So you can control everything that is generated with, using these configurations. So we need to create a key for this one. So this is how you create one. For example, we are going to create one for our parameters. So we need a parameter first. It's created as a case class, so we can just create a case class. Fuck, sorry. No, cancel console. Case class and SDRAM config, something like this. Then we do our parameters here, and some calculated ones maybe later. So the address will be a big int, which is defaulted to the big int of maybe not defaulted. No, we are going to make this one mandatory, and the size of this. Oh my god, I don't know exactly which one we are going to use. I don't know which one exactly we are going to use. So maybe we need to make it in a way that it will work for all of the stuff that we are going to do. It just that happens that we can encounter any type of size of memory, you know. So if we put directly like a size, like for example just size of begin, can be any size, and that is simply not true for the SDRAM. But I think for now we are going to put it there, but we are going to put a number here. So for example, like I don't know, it's 256 megabytes. The one that we have in the ULX is 256 megabytes. So the one in 256 megabytes is in the system. So 256 megabytes. So one gigabyte is, I think if I'm not mistaken, is 10 million L, but I can be mistaken. It's 256. It's a quarter of a gigabyte, and the whole space of 32 bits has 4 gigabytes. So it's a 16th. Yes, there's a 16th. So I'm going to put it at 1/16 of 32-bit. We have quite a lot. And I think this will be that's going to be all for it. So now we can do our key. So let's do the key. The key is just a classification for fields that is going to have the SDRAM config. But in the field, now the field we need to extract it from here. I think is it's from config, from the general configuration structure of the rocket ship. This is the field. Okay. And obviously this is not a UART key, we have a SDRAM key. Look at that. Okay, we are ready to go. Now we are going to start creating the actual memory. Let me just console here. How did I did before? Because this is not a typical black box. I know that I need to create something like this. So I know that it's class, for example, SDRAM extend lazy model. I need to create a lazy model and a model inside. So this is a diplomacy. Then I know that I need to create okay, I need implicit parameters. And then come on, import class, but it's not in the config. Okay, I need to export all of the configs. Then I know that I need to create a lazy bound module, which is equals to module of new model of new lazy model implementation, and the wrapper is going to be this. This is how you create a lazy model. So the lazy models, they are actually based of having multi-IO models. That means that they are not strictly necessary to have an IO like this one, but you can have IOs. So we are going to create only one IO for our stuff, which is for the SDRAM, which is equals to IO of new bundle with this exact stuff, with the SDRAM, it has SDRAM, and we created our port. As for our model, so you can only create models like regular models inside of this lazy model implementation. Lazy model implementation is a regular model. Lazy model is the one that handles all the configuration before the model is created. That's why it's named lazy model. So we're going to create just the SDRAM implementation, which is going to be a module of new SDRAM. we need a configuration. So this is going to be SD and BBCFG with all of this. So we are going to put it for now by default, and we will see if we need to add more configurations here to make it here, or maybe put all the configurations just here. I mean, we can just put like something like this CFG, something like this. Yeah, equals this. Literally, we can put this, and and this is completely valid, and we can import it from our stuff. So that means that we need to be input by a general configuration of this. So CFG is going to be the SDRAM config, and this needs to be supplied. And we are going to use here the SDCFG.SDCFG. So again, this remember that from this point on we are creating our periphery. This is only the periphery, so this configuration is for the periphery. This is not the same configuration of the SDRAM. That is the one that you use for, you know, implementing your stuff. Sorry, I need to check this. And now we are going to do okay, we have our implementation, so we are going to just connect the SDRAM port that we just created to the SDRAM implementation dot .io. No, shit, I don't have it like explicit. I need to connect it manually. No, I cannot do this like quick. That's well, that means that we need to do it manually. No problem. This is not a big deal. So we need to put like each one of them, like this. For example, the SDRAM clock, for example. Clock O goes to SDRAM implementation clock .io dot SDRAM clock O. And then CKE, CS, the RAS here. You know, this is how it goes. Cast, WWE, DQM with DQM. Other BA, all were outputs. Now for attachments you need to use attach system here, which is composed of two stuff. Now attach is an experimental. Come on, give me the experimental one. Fuck you then. Okay, I will handle it here. So As for this is not a bool, so it's with a data IO. Okay, perfect. And this is how you do it with the configuration, with the stuff. Now we need to create a slave. That's how this is done. So the way that you create this is creating a node, and for creating a node you need to do it in the lazy model. So this is what is real, I mean this is what is hardware, and this is only configurations. So for configurations we are going to use maybe the configuration, the tiling config, and I know for a fact that is something like the we need to implement tiler link. So this is tiler link, and we need tiler link what slave parameters, I think that version 1. Okay, yeah, now I remember. And this is the configuration that you put here. So address is going to be the address set that misalignment of the address, the configuration address, and the size. And we need to supply a lot of more stuff. It's just that I don't have the scope right now of what is needed to create a peripheral. So let me just cheat here a little. I have something here that maybe it will be used for this. Then okay, I now remember. I need to I need to deal with this stuff here. So you need to basically supply all of this. This is typical for a single one. Again, transfer sizes, the stuff here, the RISC executable, the region type, the device actually, and the address set that we just put here. So this puts the address set, the address span, which is going to span through address and the size. The reason why it's misaligned is because if we only put an address set, it's expecting a mask. So the misalignment will convert all the address and size with the aligned masking pairs. The device, we are going to do the device, but let's wait for now. I know that the device is something just like this. So I know the val device is equals to memory device. Actually, I think it's new memory interface, memory device. Yeah, just like that. It's pretty simple. It's just memory device. And we put it here, and we put it here. Now, this region says that it's getFX, that is not cacheable, which is not true. We are going to put it uncached, which will pull it cacheable. Yeah, I don't know how this works. There's literally a name named cached. That means that maybe whatever goes out of this slave, it will be cached afterwards. Because definitely we want that this memory is cacheable. Yeah, I don't get it as well. Okay, transfer size. So we only support 1 to 4. Why 1 to 4? Because the interface of the wishbone supports up to 32 bits, and it has 4 selections. That means that supports 1 byte and up to 4 bytes. So this is strictly our stuff. Now, this is executable true, because if we don't put it executable, that means that whatever we put into this memory won't be able to be executed. Then we need to do this is the TinyLink configuration now. Now the TinyLink port configuration, which is a little different. Yeah, it's a little different. It's a TinyLink slave port parameters. We need to do this. I mean that version 1, which is a sequence. Is a sequence of slave parameters. So we have one here. So we need to put this in a sequence, because maybe there's several. So it's a sequence of this with the bit bytes. Simple enough. So managers is this, and the other one is the bit bytes, which is strictly 4. Why again? Because this is a plus of 32 bits. So again, this is logical. I mean, this is the number of transfers that can support, and can only support 1 to 4, nothing else. Now, for the bit bytes, that is the port. That's why it's named port parameters. The port will support like 4 bytes in TinyLink. And then we get our node. Finally, well, node, this will represent the peripheral by itself. And this will be and the node will be the TinyLink manager node of the sequence of the parameter of the configuration that we just created. As for the connection, I think well, this is our SDRAM node. No, this actually that is going to control the SDRAM, but we are going to make the some stuff here. We are going to create val node, which is going to be the TinyLink buffer. I use a regular TinyLink buffer. And what it does is just buffers the transactions, like delays like 2 or 3 clock cycles in a FIFO. This is for timing, more or less. But then we need to do the connections to the node. So the connections will be something like this. The SDRAM node will be connected. Well, you usually just connect it to the node, no? Yeah, like it's going to be a TinyLink buffer, and it's going to be connected to the SDRAM model, to the SDRAM node, just like that. But then there's a problem. The problem is that outside of this node, what is going to happen is that can be a possibility that maybe 64 bits or 128 bits, and the transactions usually support like a lot more, like 64 or 128 bytes per burst. That means that we cannot handle all of that, not at all. So we need to do 2 things. First of all, is we are going to put a TinyLink widget widget. So what it does is whatever is connected from here now on will have this the size, and this can be any size. So we are going to put here 4. Wait, I think it was the opposite. Let me check it real quick. Yes, it's the opposite. That means that this goes with the with whatever is connected to, but we don't know yet what is the size of the of this thing. Okay. That means that we need to supply into the configurations, not this configuration, but just strictly for instantiating this SDRAM, we need a block bytes and a bit bytes. So this is the bit bytes. Whatever bit bytes we have here, we are going to supply it according to the configuration that came from the system. So the node will see that, and it will connect it to the bit bytes 4 afterwards. So this side is 4 and this side is whatever. Now here comes the second one, and notice that I also put block bytes. So this is because we are going to also put a TL fragmenter. So the transactions, right? The transactions can come in this kind of sizes, but sometimes it can go like 128 or 116, and we only can support up to 4. So that's why we need that fragmenter. So a transaction of 128, for example, it will divide it in 32 transactions of 4 bits or 4 bytes, sorry. And that's how it works. So we need to supply it. Let me cheat a little. The minimum, we need to put the minimum size here, which is 1, and the block bytes that is the maximum that this side can support. And we just beat it. Now, when we have our system, we connect to this node, not this node because it's already connected. We connect it to the buffer, and this is connected. And now, so this is the SDRAM side. We are now going to connect the wishbone side. But before that, we are going to connect the clock and reset now. So the clock and reset is very simple. So like SDRAM implementation.io.crki is going to be equals to the clock. Same for the reset. Perfect. WB side. Now we need to convert the stuff here, but we need to before that we need to obtain the title link. So I have a little cheat here for this, for obtaining the bundle. So you create here we obtain this from this node the title link. So this will symbolize the bundle. As you can see, is a bundle, and the edge is the connection by itself. Maybe we need the connection. We will see, and we will be connecting that. Now I have a flow here, and it's going to be like very complicated to actually understand, but I will try to do my best. First of all, we are not going to support any of the secondary channels, B, C, E. No, we are nothing about that. Now we need to actually like start doing the stuff, no? So strobe and CEC. What was before? I don't remember. sorry, I need to cheat it because I don't know. I don't remember. So in this one that I implemented, I used only the strobe. That was the problem. I don't have the CGC. But in this case, the CGC and the strobe can be together, right? So the CGC and the strobe are the same. I think they could be. You know, we are not doing this very well. So I will do it like wishbone with a specification. We'll search about that. And we save it. The wishbone signal descriptions and use of a strobe. Most qualified following signals. So CGC needs to be asserted during the entire transfer cycle. So what is the difference between, what I want to know is the difference between the strobe and the CGC. So CGC is the one who selects probably, but what I want to know what a strobe does. If a master doesn't generate wave states, then STBO and CGCO can be assigned to the same signal. If a master, but I am not a master, I'm a slave. Single read, single write cycles, block read, block write cycles. So CGC, the strobe, CGC, and the acknowledge, I think they are the same. I mean, yeah, I know that there are some for mastering data, like for mastering, for having an easy to build arbiter. This thing is not necessary. But if it's a slave, it's okay. So I'm going to assign it to the same signal. That means so in the interface that I had before, I have an acknowledge, right? I have an acknowledge, yes. Wait, give me a minute because I don't remember. I don't remember this protocol, this tiling protocol. Maybe we can just like connect it directly. Yeah, let's do it connect it right directly, and maybe we will figure it later. Maybe it won't work the first time, but we don't care. So SDRAM, right? SDRAM implementation. We have to connect all the wishbone interface. So a strobe, no? A strobe I will be, if I'm not mistaken, it's going to be the tile link in. Ah, wait. Now I remember. Now I remember. Yes, wishbone is more easy than tiling. Tiling has two channels, because it's A and valid. So we cannot just like put this in valid and wait for the ready. Not because it's not. There is no such thing. We need to buffer it. So we need to buffer it at least once. So we are going to have a flow control. I have a template for flow control here. So then full that we have a transaction. We have the valid held, the size, the source, and the hash data. Okay. Now we are going to put this here. We need to activate this when the address comes. Okay. So shit, this is difficult. Okay, so I have this code here. Yeah, this is very basic. I mean, not for you probably. I'm going to explain this. So this when fire the channel and fire the A channel. So I'm going to do it in order, which is better. No, but I'm going to leave it there because maybe the order will mess it up. So the fire means literally that the ready and the valid are both in asserted. That is what means a fire. I can just literally put d.valid, d.ready, and ampersand together, and you will have the fire. When we have a transaction in the D, like complete handshake, we say that we don't have a transaction pending. But if it comes something from the A, that means that we need to do a transaction. Okay, ready for that. Now, so the next thing is to actually, like, respond to the data channel with the valid held. This is if we already did the transaction in wishbone and we are waiting for the D channel to respond. This will be default, right? Wait, no. What if we make the transaction go through, I mean, we can put the transaction into the A channel responds similar like the wishbone. Yeah, let's do it like that, but we still need to hold the value. That's our stuff. So we only need to care about this data out and this is style out. We still don't know what is style does. What is a style? There is no such thing as stall. I can choose to ignore it. Stall is connected to something here. Asset wishbone command in read or write states. Wait, what? We have a stall and we have an enlargement. Why not just use ACK for that? When the state is not read or not write 0. What about the ACK? The ACK is 0, and if it stays right, Q and relatency. Maybe we don't need to obey this signal, which is weird. Okay, so I'm going to tell you what we are going to do. We are going to leave this like this. So the strobe and the CGC are the same, and they are put into the A channel. So my idea is to actually connect the A channel to the wishbone, because it has the same handshake. So the A channel will be there. Then as for the valid held, that means that we have so we're going to do the transaction the same way. So that means that the ACK-O goes to the ready, like literally just goes to the ready. So that's the same. Is the same, exactly same handshake. We need to probably. I mean, we need to also put the address. The address is maybe TL in bits and address. So this goes here. So we're going to replicate the bits as best as I can. So the address is here. Now the data, no? We need to do the data, and we know that this is bits.data maybe. Okay, we have this. We have the write enable. We know this with a write transaction. So we know that SDRAM implementation.io write enable it equals this. That's why we need the edge. to know if he has the data. Literally, they just check about this. Okay. Now, okay, stroke ready enable cell. We still not have the cell. This is going to be a little difficult because, I mean, Tyler link in dot a dot size bits. I mean, they have a mask. What about the size? It's just a mask, right? So that means that is a mask. It's a regular mask for the data. So we're going to put it into the selection because that is a function of that, literally. Cell CC address data. Data O is star O and echo. So ACK is not here. We need to only handle the ACK data O and ACK O. Then we need to save our data. Save data. Now we are going to save. The next step is to save relevant information from A to the response in D. So the way that we are going to do this is I mean, we have this thing here. Has data is something like this, but then we put it here. This kind of stuff. So all of this are registers, right? So only when we have a transaction in A, we save our relevant information here. The size to the size, the source to the source, and data to data. Easy enough. But then we need to respond with the data. We need to save the data as well. So when this fires, because it's the same event, so doing this a.fire is going to be the same as also doing the CGC and ACK. That means that we can save our data here for the future response. So what we are going to save? Yes, the same old. This one, the data over here. Response characteristics. Now we need to respond accordingly, and we need to respond whenever it's here. Okay, let's start responding to the beam. So there's two that I have here that is about the bits and the stuff. So we want to do an acknowledge of the source that says at the data. This is the reason why we needed to save all of this. The source, the size of the data is necessary to populate the bits. As for the opcode, if we had data before, that means that it was a write. We need to do access acknowledge or access acknowledge with data. That's the stuff there. And we need to start to respond to the D like the D valid when the valid is held. So I have this piece of code here. Actually, this default, I mean, we can use default. Maybe we can just use this one. Okay. So the transaction of the D, the response to the D is not like this. So the D is going to be default. So we have something like here. What about the ready? I mean, we are already taking in care already when it comes here. So when it comes, the a.fire is going to be full, and when it comes d.fire, it will put it false. Actually, it's more convenient if I put it here, so it can have a little of order. So you have the hash data, that is this. Then we connect the A channel directly to the wishbone. Then save. Then when that happens, the relevant information to this registers here for the D. Then we do the dynamic of the false true. Then respond to D accordingly. But that means that we cannot accept data. We cannot accept data when it's full. So we need to be careful and not trigger the annex stuff until this gets, like, you know, the A and D is already done. Okay, I think like this it will work. I mean, it probably won't work, but something like that. The important thing for you is that we learn how to do this, then we learn how to obtain the tile link, then we obtain the catalog link and do funny connections, the SDRAM stuff, the clock stuff, and that kind of stuff. So you don't actually have to worry too much about it. I will probably need to like iterate this code a lot and see in simulations if it's working, but probably it will work like that. Again, this is not an easy thing to do, so it's understandable if you don't get it at the first time, but it's something like this. The thing is that this code will work, and you know that it has an A channel, and the A channel I connected directly to the wishbone, then capture the data. Then when we have the data with this is A fire, we put it into the D. Then this thing is not going to respond when we have a transaction that is not fully totally done. That's how it works. Now we are ready to just like connect it to the system. So I am going to do just that. So there's a lot of shenanigans here. I mean, like a lot, like a lot of shenanigans here. I literally copy this from you copy this from any peripheral. So we are going to use a peripheral here in the chip, for example. So generators, all are inside of sci-fi blocks, sorry, or cache. Scala, maybe the devices, or maybe the, let's see, the GPIO, and they have this thing named periphery. Yeah. And we move to the opposite, and we need to do this. So it's for, you know, when you have the system. Remember this, has periphery, GPIO has periphery, or has whatever, has this thing. Those are this kind of things, is implementation of this, and it's an attach. And the attachment also is a little quite complicated, but it's not that complicated. It's a bunch of formalism, and we don't think that we need all of that, but maybe we are willing to. Like the attached parameters, yes, and they have like the clock domain stuff, and which boost do you want to attach it, which a lot of things in a lot of stuff we actually don't need, so we are going to just do it ourselves. But we definitely will want to do the attached parameters, so we are going to create first that one. So case class SDRAM attach parameters, yeah, which has the, you know, the device, this is the SDRAM config. Where the where is going to be always the M bus, so we don't need this at all. The blocker address, I think we don't need it. The clock blocker, no, we don't need a clock blocker. But the control X type, maybe we need this. And interruptions, we don't know, we don't need interruptions, at least not for this SRAM yet. So we only implement this, but this goes here. Then we put our SDRAM here. Pretty easy. They have something like the next ID or something like that here. We can just put it there if you want. About where's definitely the next ID? Oh wait. We need this, so we are going to just create it. And then we are going to just start doing the stuff. So we need the name, no? The name is going to be not GPIO, but SDRAM, and there's going to be the SDRAM object next ID. Perfect. CBus, no, we are the MBus. Well, MBus is equals to where located to the grapher of the MBus. There you go. a clock domain wrapper, which is going to be the clock domain wrapper. And these things. We need only the clock sync domain. So this obviously not a GPIO. This is going to be the SDRAM, and whatever is here it is, and then the SDRAM here, and this is an SDRAM, and this is an SDRAM, and this is not a total GPIO. This is a SDRAM. And to stop this one, to actually stop giving me headache, I'm going to put it in the end this RAM. Okay, it goes to the MBus. So MBus dot DRAM something. I don't remember. Attach. I mean, it's not coupled to the RAM controller. Yes. I think we will put here as and domain. And no. Then I need to do the stuff here. Now this is on a string, but it's waiting for an option. Okay. So some. And we need to put all of this bullshit here. This is for interrupts, this is for the stuff. So we don't need a blocker again. We need only this actually. Yes, we need a clock block. Okay, so this is not a GPIO domain deck wrapper. This is thing. This is synchronous. We will try to do it with the MBus. This is the SD map with the SDRAM.device. Perfect. This is the synchronous design. Oh wait, this is MBus. This goes to rational crossing. What about synchronous crossing? So synchronous crossing goes to GPIO clock group. Just no, this is the SDRAM clock group. The where, then the blocker. We don't need the blocker. You need only this, the clock group. Perfect. Because we don't have a blocker. Okay. X thing, which is this, and the bus is connected to the fragmenter. But we already had a fragmenter inside. So we only need to connect it to our node, no? Like the bus connected to the node equals the bus. Because the fragmenter and all those kinds of stuff are not there. We already did a fragmenter before, and we don't need to control X sync. It's just a node. something is wrong here. What does this DRAM controller? It has a TL widget with TL buffer and overall attached to. Then I need to do is an attach, you know, a regular attach maybe. Maybe you need to do a couple too instead of to the RAM controller. Okay, I will do it with regular this thing, because we are not going to do it with the DRAM controller, because the DRAM controller is just like you saw. It's just like a buffer, and it creates the tiling with a widget, and that's it. Doesn't have anything else. It's nothing special. So if I do a couple 2, it's going to be the same. Couple 2 is it just creates the L1 node. Okay, we are ready to go. And now this is not C bus, this is an M bus. Okay, the SDRAM needs to be device, then block bytes and bit bytes, no? It was in that order? I don't remember. Block and bits. Block and bits. Okay, perfect. We are ready to go. Now for the periphery we need to just do this again. We already created our key, which was here. I'm going to put it a little down so it's a little visible, and it has the same kind of stuff, you know. Then we need to do the has something. Okay, the basic system only. It has periphery, has SDRAM. So SDRAM nodes equals to the SDRAM key of this, and we do the SDRAM parameters of PS attached to this .io .looking. Then I do this. But then SDRAM, this is not a node, this is an SDRAM, like literally an SDRAM. Then I need to do the implementation, which is this one. Put it here. We has bundle, no, only the lazy model implementation. The outer has to be compatible with the has DRAM. Now outer that SDRAM set with index case NI. This is the SDRAM IO. No? SDRAM IO is for each one of the stuff we are going to export our port, which is well, IO is equals to IO of new SD and then bundle with this thing, you know, with the interface. It's the same that we put here. Look. Actually, we can just create a a bundle that that is just this thing, something like class SDRAM if extends bundle with this bullshit. Yeah, only that. Then, to be more comprehensible, maybe it's better to put it right there. And do the same here instead of putting bundle of stuff. Better. It's better this way. And so SDRAM .io, not dot model. No, this is n. And SDRAM node, no, make me model dot SDRAM is connected to the IO that we just created, and we return the IO to be exposed, and that's it. Now this is not has periphery PPIO, this is a has SDRAM model implementation. Holy shit, this was hard. It's always like this, no? I mean, yeah, that is the point. If you are watching this, probably it's because you are interested into this. And maybe you are stuck with some kind of engineering using this godforsaken language. Yeah, very much it. Now we're ready, no? I mean, we can just put into the system. Wait, what? No. Oh, this one. Ready here. And now we need to do it one down. The other one. Perfect. Holy moly. Okay. Now we need to do it in our stuff. So we have until the system. We need to do it in our platform, which may or may not have an SD stuff. So well, or the output, the SDRAM port, possible ports are going to be here. So while SDRAM is equals to P of this key. Wait, I left it. The map, which is an A of a new SDRAM IO. We connect it to the side. Oh wait, there is a sequence of any. Wait, what? Type annotation, please. This is not a sequence of any. I need a sequence of SDRAM IF. Ah, wait, I'm stupid. That's why it was not working. Okay. is a map of pulses which will go to connect the port to the ready for that. So as for the you're not going nothing into the harness, so the last step is to just do it in the shell. Okay, we are right here finally. So we need the ULS3X manual. Wait, it's the ULX3S. What's the opposite? 3S. Sorry. So okay, what about it will be useful if you give me the constraint maybe. Where's the SDRAM? Ah, okay. Here is the SDRAM. All of this is the SDRAM. Now, in the configuration files, sorry, I need to put this here. In the configuration files is something like that. Oh wait, first I don't have it here. RISC-V console. So FPA, ULX, and this one. I already have it here. Ah well, I have it, but it's commented. So let's uncomment it, shall we? So perfect. Now the problem with this is that I mean A, BA, QTQM, all of them are written like this, which is a little inconvenient. I wonder if this supports just regular vectors. So for example, if I take for example on this A on the score, I can put it in the A, something like this. I do it. Now if I have like a number and a quote, the regular expression is the capture one plus is the capture one with this thing and the quote as well. You can find it? Yes, but it's a little bad. Let's see with S. Okay, maybe like this. Okay, find the place. Actually, from this point on, why not just do it for the rest of stuff? You know, this square parenthesis stuff. Ah shit, but kinda need to remove the underscore. Ah, my love. Very difficult to do this. Why am I doing this? Why I'm killing myself? Why? Why did I study this? Why do I even exist? Okay, I think we are ready. I mean, most of it. Yeah, seems good. Good enough. So, I know that is like this, but we need to make it in the same fashion that is here, no? So, for example, this is named CLKO, this is named CKO. Yeah, that kind of stuff. Yeah. So the renaming shouldn't be. I want to make the renaming a little, a little easier to do. A little easier. Just a little, just a little easier. So something like this. I know that for a fact that if I put this and I put it twice, it'll be like this. Yes, because the port I'm going to call it the SDRAM. Now this is CLKO. Ah, shit. The CLKO, CKAO, NO, WNO, RISC-O, CAS-NO. Oh wait, we have it like this. CSNWEN, the CSN. Wait a minute, this is logic. This is negate logic, or this is not. I fucking shit decide already. So the CLK, CKE, CSWE, CAS, RAS, A, or they call it address O. The other one is BAO. The QMO. And this name it D. This is data IO. That's good. That's good. That's good. Okay. Then we are ready. Got CLKey, CKE, CS, RAS, CAS, adder, BA, BA. Okay, that's good. It seems good. Good. Good enough. So we put it in our LPF. So what about the shell? The shell is going to be stupid easy because it's literally just GPIO of the new SDRAM IF. Like literally. As long as we put SDRAM here. Literally is that. and the connection to them to the actual stuff is going to be the same as well. So SDRAM is going to be the platform.io dot SDRAM. I mean, it's a sequence of SDRAM. Okay, so head. I'm ready. We are ready. Almost, no? I mean, we'll still need to, put it into the memory, into the configuration. So for the configuration, we are going to put it here. Just another case. But this case is named for the key that we just created. So this is a new RAM config. In address, I'm going to put in the 9 million, and the size is going to be like always, and the configuration is going to be default. There you go. Okay, that's it. Wow. I mean, let's see. Let's see if it generates the Verilog first. And we'll sit down and see what happens. If it doesn't happen, it's okay. Okay, it's not working. Cannot be applied to big int. That means that we need to convert it to int, probably. What if we just put this into int? I mean, it's not that big, and we only did big ints because it was stuff there. Come on. Well, if you want to, I don't care. So that is easy to fix. It's a matter of putting it back in. Or it was in different. It was in the platform. It was not there. Shit, I did it wrong. No, it was in the platform. So that means that this is back init of this. This is the back init. Yeah. Okay, again. Let me see. Like element, this thing will be hardware, not just set time. Maybe I forgot to put it in IO. Or in which line? 1.28. I need to put it in a no. Eighteen, 17, 28, 17, 28, 17. So it's not creating me the bundles. I mean, they are creating them, but the big element should be hardware and not chisel type. But if I wrap it in an IO, it doesn't have any sense. You know, instead of doing that, what if I just do a vec of this dot size, then near GPIO. Yeah, that is certainly easier. But I wonder, it's the same, no? I mean, more or less. K not found, the location of MBus doesn't exist because I put the system, the configuration of the system in a very simple one, probably. Current post topology does this. So what about not location of system and bus? So that means that I didn't put this. But yeah, I mean that's kind of the question. But then I need to. I think maybe I need to put it into the. I need to search for the. Ah, come on! What is wrong with this? Ah, shit. What is that? What is that? What is the problem? I know the problem. It cannot locate this. That means it didn't got created. I understand that. I understand that. But I don't know how to fix it exactly. So maybe I need to go to the system, to the subsystem, to the basis system, and see what the hell happened to the MBus. So leave it both, get on S, get on else. supposed to be always in this bus. So the system is TL network topology, maybe. TL topology. So is the topology located? Problem. Can instantiate within context that has the name locations. What the? What the? What the hell is that? It's a case class, so it's a network topology. But then what? That means that the system can configure that. I know that I can understand that. It's just that has configurable TL technology, so that means that something is here. What location is hierarchical location? So topology is the topology of topology locator of location. Then I do the instantiations, and for each it does the connect. Yes, I know. Extends field of sequence of can instantiate within context. No, that means that we need to search for something like this. With ring system bus. Okay. So this should be a configuration that enables me the M bus. So test chip, basic system, but the cases, there's so many less they're supposed to. With just one bus. Just one bus technology parameters. With incoherent bus topology. With coherent bus topology. The M bus. I think the problem is the M bus. So that means that the incoherent doesn't get an external memory. I need to create a coherent. Crap. Hopefully it doesn't broke things. I'm going to do it coherent then. with broadcast auto. Crap. Oh no. It's going to be a ride. Let's see if it's good. Let's see if it works. Second time. Cannot model without instantiated model in SDRAM scala 11, 111. So Okay, that model. No. The lazy model implementation is something like that, no? No? No, it's not like that. Okay. It's because it's not needed. I remember. Requirement filed for the TL fragmenter with parent sum. Can't support fragmenting 1 to subbit 4 accesses. どういうこと? Can support fragmenting 1 to 4. Holy moly, what is this? This is definitely definitely what the hell moment. So it failed in the fragmenter in A7, so I'm going to fragmenter A7. I know that is in the timeline maybe. '87, so mean size is more than bit bytes. Does not can support fragmenting mean size to subbit bit bytes. So the mean size is, when I put the fragmenter, it is the first one, then the max size. 444. If I put it equal, maybe it's okay. Let's see. Maybe if that is the case, maybe we can just put it in block bytes. Point in case that doesn't support burst. If not, I'm going to remove the burst from that. No, definitely I need to not fragment. Okay, let's try to not fragment the transactions. Hopefully like that is okay. So no. Wow, what do we do here? All managers behind Dell to remove support are quite big, but SDRAM only supports this. So I definitely need a fragmenter. Okay, I need to know very well what a fragmenter does. Shipyard. Okay. Mm-hmm. Okay, mean size is the minimum size of the transfer supported by all our managers. Old-worn goes in and goes out. Okay, so the minimum size is 4, definitely. So it's 4. The block bytes is after the fragmenter is applied. Okay, maybe like this, okay. 4 block bytes. Let's see. Still fails. Let's see. Okay, this is an interconnection problem. SDRAM in the 118. It's an input, right? Maybe it was just oh my god, this is boring. This work. But that is the fun. Oh, almost. Shit. Connection between left and source. Left or right unavailable. Okay, so in hard RAM model implementation of this RAM 224. 234. Let's see. So one of these two are not created yet. That's the problem. Maybe like this. Okay, it says not available. No, not because of that. I think maybe I can cheat it from here. But it's just a bundle. So the bundle gets clonated using this. It's the same as me doing this. So what the hell? It says that it's not available. And that is not that one, it's this one. Okay, chisel exception. Connection between left, that is this in IO in elaborated this, and source. I use the RAM and this RAM. Left or right unavailable. So this is the one that is not available in the RISC-V system. Maybe I need to create it first. I create first the IO, then connect it. I mean, we can do that, but What is the deal? For example, they use something like this. No, it's the only thing that is there. Hmm. Okay. You know what I'm going to do is just I'm going to do this only like map, and in this case wait, it's better to just do vec init, right? No, vec of folder.sdram dot size, then new distribution this and IO. Then we can just do this, zip it with SDRAM IO, and just connect it to the IO. Be like this is better. I'm not sure if it's going to work. And if we have different kind of SD memories at the next time, it's going to be a mess. But yeah, that is unsupported thing from that thing. No, it's still bad. What the hell? Look at this. It's supposed to be available. Yeah. But what happened? Like, what happened? I don't get it. I literally don't get it. Now we are stuck here doing iterations. I hate this. I hate it when this happens. 仕方ないですね。I mean, we created this, but then it's failing in the line 224, and it says that doesn't exist. What doesn't exist? BAO. But BAO is just we cannot do it like this. If that is the case, that means that this is directly an SDRAM wave. No, it's the same. It's the same. It's exactly the same. So what is happening? But it's supposed to be available. I mean, it is though. For the system. The system has SDRAM and the SDRAM model implementation, and this is the detected implementation of this. So that doesn't have any sense. What about the platform? What if it's a platform problem? Okay. If a platform problem maybe is here in the platform. So model location, model of model. So I connect this to this, and this is supposed to be thing. No? No idea. No idea. I am blank here. Shit. Shit. Don't know what is happening. If somebody has a clue, I will be eager to answer, but there's nothing in the chat. Okay, so the problem is that it has SDRAM, but when it tries to do the SDRAM module implementation, it creates the I/O. It says that it's there. It says this, that left or right isn't available. How did I do it before? It's not supposed to be difficult. Okay, let's see what I did in other stuff. I mean, I usually do the make IO. Yeah, I usually do the make IO, but that is not the way. What if we copy the one that is in this bullshit here? Maybe if I copy from the platform the one that comes from the but where is it? Maybe choose the order. Which shall I create it here? If I create it here, I don't think it's going to influence anything. I mean, I literally do the same thing. I did it for the PCIe. I don't think it's going to fix it. Yeah. What the problem is attached to? You mean I doubt it? Connection between left and right. I'm doing something wrong. I don't know. Aquí. No, I will say that I have literally no clue what is happening. I mean, it's okay. It's supposed to have like this. Yes, the SDRAM is already there, and I connected to the system. But then uh, some kind of, yeah, like this one or that or the other one or something is getting not created. Happens exclusively with the BAIO. If that's the case, maybe we can just cheat it instead of using the see which one is not being created. Yes, we need to cheat it, and the way that we cheat it is like this. So instead of connecting using the direct, the easy version, we connected using the hard way. I mean, we don't have anything else to do, so we need to search and see if it's here. So it is IO. So it's IO in this side. Come on. And the other one is model. Maybe model that SDRAM. Okay, let's try it again. Yeah, we don't have a way to do it. The sync or source is elaborating in the current model. $234. CKI. Let's see. which let's see which side is the one that is definitely failing. Okay, it's definitely this. I mean, it's impossible that this is not being created. The SDRAM is definitely the one that is failing to get me a model. Maybe if I name it IO, will be better. It is not supposed to, no? I mean, yeah. I've done this fashion as well. Let's call it an IO. Let's call it IO. If it is like that, then I need to do it as well Yes. No, definitely the problem is in the is not here. It's not the creation of this vector. Is up. Whatever I put here is wrong, and it's wrong AF. What did I do wrong? I mean, the I/O is just an I/O of the SDRAM interface. Then I connect it. That's it. Maybe it's because I forgot to do any other stuff. Like, I don't know, connect this properly. What if I need to put the blocker? Probably will fail, so I'm going to see if it's something else. Look at this. I mean, it shouldn't be a problem. And the lazy model is almost certainly not a problem as well. No, still. This one is not getting created. Just it can be anywhere. don't know what happened. Hmm. Turn into 7 again. No, this is not existent. Can you put into this one? I want to print them. Fuck this shit. I need to create an IO node? But why? That doesn't have any sense. Ah, shit, let's create a fucking node. It's better that than actually doing something. So the register router, how this creates this set. So it creates the IO node and creates the port. This is port bundle and clone type. And the port bundle is supposed to be this thing. So I need this. Okay, so we need to do the port bundle dot clone type. So thing here is we need to do the new bundle, new SDRAM IF and clone type. And this is the this is our stuff. Okay, so if I use this, that means I need to stop using this, and maybe use the same resource that this one's used for getting the IO. Port, yeah, use port. Perfect. If that's the case, that means that I need to do the SDRAM nodes equals dot IO node dot make sync. Then the SDRAM IO is going to be the SDRAM, and the same as this bullshit. Perfect. Don't know what happened. That is supposed to work. I mean, that's the way that it works. But I did it just like wrapper for doing nodes. So it's just wrapping into nodes. That doesn't have any sense. Yeah, that was the problem. I mean, I solved that problem using that, and that doesn't have any sense. Okay, I will see afterwards. What I'm going to do next is just some compatibility stuff. So, for example, we only did it for the for the U. That means that that the other version doesn't support that. Yeah, this board doesn't support that. That's why we put it like this. Okay, this worked. I mean, it's generating the overlap. Finally, okay. So I'm going to check the same for the arrow, but it's a new FPGA. It works. Okay, so I'm going to push this and we're done. Okay, it was not what I expected to be, but it's working. So that was it. Hope you like this video. I'm going to do some tests regarding if it works actually in the SD card in the SDRAM. Hopefully it works like a charm. So thank you very much. I'm going to finish the transmission right now.